geometric sequences. So in the kind of previous video, I talked about arithmetic sequences. So when the sequence, what happens from term to term, you're just going to have a constant addition or a subtraction from one term to another. I'll put up a link up above there to the arithmetic sequences. Now the geometric sequence is kind of similar. The only thing is that instead of adding or subtracting from one term to another, you basically find that you are multiplying by a particular number to go from one term to another. So for instance, for any geometric sequence, if you have a set of numbers that are given to you, so let's say I'll start off with our first term. Let's say, we're going to start off with 3. Now, if you wanted to go to the second term, and let's say I wanted to multiply, okay, let's say this by 2. So I'm going to get 6 right here. So this would have been my term 1. This would have been my term 2. And we continue this pattern, right? So we're going to be continuously multiplying. So this would have been 12 and so on. So this would have been term 3. So that's kind of what geometric sequences are all about. It is when you are given a particular sequence of numbers, so these terms, and then you notice that going from one term to another, they are basically just ratios of each other. So for instance, if I take t2 and I divide it by t1, I will get 2. If I take t3 and divide it by t2, so if I take any two consecutive terms, I'm going to get the exact same ratio between them. And that ratio can be both positive or negative. It can be a fraction, it can be a decimal, it doesn't really matter. Most of the time when you're just starting this, the ratio is going to be some whole number, but overall it really does not matter. So as long as this ratio is some kind of a number, both either positive or negative, it can be fraction or decimal, then you are dealing with a geometric sequence. Now, like in the arithmetic sequences, we do kind of want to try to find the general term, right? So if we keep going, what would have been the general term right here? And for that n, okay, where it could be, let's say 10 or 20 or 100, can we actually find that particular general term expression? And the answer is yes. And you can, again, find it, one of two ways. There's a recursive way of finding that sequence. Now, the recursive way, going from one term to another, okay, so that is, if you're going and you're noticing, in this case, I'm going to take this sequence, and if I am kind of multiplying by 2 every single time, then really, my term Tn is going to be equal to, I can take the multiplication, so in this case, the factor is 2, and then take my previous term, Tn minus 1, whatever it was, and I would have found my next sequence. Now, this would have been, of course, defined for only natural numbers, and n is going to be actually greater than 2 here. So this is what we're going to have, and it's going to be greater or equal to 2. We don't want it equal to 1, because if we set it to 1, that t 1 minus 1 would have been t0, and we don't have a term t0. We started off with term 1. So, this is kind of the pattern that we would have been seeing recursively, right? Now, we don't always want to have these recursive patterns because we want to, we don't want to know the previous term all the time. Like, what if we wanted just to know, the 10th term or the 20th term, just like we did with the arithmetic sequences? Then, how would we find it? Well, you can actually find this out. And it's very similar to the arithmetic sequence pattern that you're finding. So your general term Tn is going to start with whatever it is that you've begun with. So your term 1, all right? Now my term 1, okay, so whatever that might be, in this case it was 3. Now I know that the next one that I find is going to be multiplied by 2, right? Now I'm going to call this, because it's a ratio, so this, ratio right here is equal to 2. So I'm going to just refer this to as R. Okay, that's going to be the ratio pattern, because for the geometric sequences, it's not just 2. It can be any number that you keep multiplying by. So here, what we're going to do is we're going to say, okay, well, we know that we would have multiplied by this ratio, so by 2, to get the next number. Now, if we wanted to multiply by, if we wanted to find the third term, we would multiply by R again, and then we would multiply by R again, right? So what we're finding is that, okay, wait a minute, okay, all we're really doing, okay, we just keep multiplying by these R's, all right? So, how many R's do we have, or how many R's are we going to put in there? And so this, okay, we can write as an exponent expression, and it's actually going to be n minus 1, all right? So, for example, if you wanted to find, okay, so your term number 1, it's going to be, t1 multiplied by r, and then it's going to be 1 minus 1, which is 0. Well, r to the 0 is just 1, which means that it's t1. If you want to find term number 2, then again, you're going to just substitute 2 for the n, and it's going to be t1 multiplied by r to 2 minus 1, which is to the 1. So you're just multiplying by that r. And you continue that pattern. So within here, so this is the actual general term for any geometric sequence, where your r right here is basically the ratio, which is the comparison between two consecutive terms. And the assumption is that it's always the same. Okay, that's what makes it a geometric sequence. Now, you can write this as a function, okay, if you want. So it would be kind of like a discrete function, where, discrete meaning that we're just, for our domain, we just have natural numbers. So you can definitely write it like this, sometimes, okay, if you want to. I'm going to drop this multiplication. I think you know what that means. And of course, n is going to be just a natural number in here. So 1, 2, 3, 4, because our domain, is not any n that we like. It has to be a natural number. So that's in general. So if I wanted to write this out for this geometric sequence, I'll kind of switch, okay, colors in here. So what we would have is that Tn would have been equal to, so it's your starting point, 3. Then my R, okay, is going to be 2, because that's my ratio between them. And it's going to be n minus 1, okay? And now you have your general expression, which you can actually find any term that you like. Now, again, you can try to graph this, okay, if you wanted to. It's going to start from 1 onwards, and notice that it is an exponential, so it's going to start kind of blowing up on us, because we're going to be multiplying by 2 all the way through, and that's something that we can do. So let's take a look at a couple of examples of these geometric sequences, and once you see this once, you kind of know what the general expression is, and then you're kind of done, right? It's not very difficult to be able to remember this. The only thing, honestly, to try to remember is don't confuse the arithmetic sequence with the geometric sequence. Fortunately, sometimes it happens to me, as well. Okay, so let's take a look and try to map these out. I'm going to try to find the general term, Tn, for both of these sequences. So how would you do it? If someone gives you this, then you want to try to find the ratio in between them, and do a few just to make sure that it is actually equal. So I'm going to take the first one. So notice I'm going to take minus 6 divided by 3, and that ratio is negative 2. All right. Now, if I take these two, so that would have been 12 divided by negative 6, it's still negative 2. If I take the negative 24 divided by 12, it's still negative 2. So what that tells me is that my first term is equal to 3. My ratio in here is actually negative 2. So yes, it could be negative. It doesn't matter. Notice that it's alternating your signs. And once you have that, then you can find the general expression. So Tn is equal to, so that is your starting point. And then, so it's going to be multiplied by r. In this case, r is -2. And you're going to put n minus 1. Now, sometimes what you will find is not everybody likes to write this n minus 1. So you can use, your knowledge of exponents. So this is going to, this is going to be the same thing as saying this, okay? Because the n minus 1, okay, so that we have, okay, so we're going to put that right there. So this is identical, and therefore it might be equal to, 3 divided by -2, and then this is -2 to the n, if you just want to have it directly as that, which means that this really is just term 1 divided by your r, okay? So if you like, you can write the general expression as well in this particular form, okay, when it is like this. And then this would have been to the n. Both are the same, but I think, this one is good enough. Let's take a look at that second one. So within here, and you can give this a try. So let's take a look. So this one looks like it's actually decreasing. Okay, so that means it's going to be a multiplication by something which is less than 1, right? So let's take a look. So if we go from here to here, we get 65 over 325. And what can that be? Let's put it in this way, and I'll reduce it. 325. That's 1/5. All right. Now going from here to here, and probably that's 1/5 as well. So let's say, well, 13 times 5. Yeah, that's 65. All right. So it looks like it's basically 1/5. Okay. And then here it's going to be 1/5. So my general term, okay, is equal to, and it's going to be the first term, so 325, multiplied by your r, which is 1/5, and then n to the -1. All right. Now, if you want to provide a domain, okay, so for this, always remember, okay, that n, is the element of natural numbers. So 1, 2, 3, 4, and so on. So that's the geometric sequence. Now, I'll plot one of these sequences for you. Okay, so I'll take out decimals. All right, so here it is. Okay, so I'm going to just kind of define. So n is equal to, so I'll put it, because I do want to have a sequence, okay, in this way. And by the way, if you want to learn how to plot these sequences, I'll put up a link up above there. I did a short video in decimals on how to do that, okay? So we always define, okay, so our n is going to be the set of these natural numbers, okay? That n that I have in there, so I'm going to set n equal to, so you can set it to whatever it is that you like, okay? So let's say I have 100 elements, okay, within there. And now we're going to have to write this as a function. So f of x is equal to, and I can take any arbitrary one that I had. So if I go back in here, let's take maybe, doesn't matter. Let's maybe take the one which kind of flip-flops. So 3, -6, okay, and so on. So that's going to be 3. So I'll do that one. It's going to be 3. Okay, so multiplied by, and it's going to be -2, okay, raised to the x minus 1. Actually, we want that in the, okay, so we'll do this, x minus 1, okay, like that. So now this is not, okay, it's not going to plot it for us yet, okay. And now to plot it in, so we want to take all the elements, substitute them into our function, okay, and notice what's going to happen is it's going to be blowing up in both directions, okay, in this way. There we have it, and it just keeps going, and it's alternating, right? Positive, negative, positive, negative. So you can plot it up like that if you wanted to. All right, so that's a plot in decimals, okay, that you can have. Now, here's an interesting question. It's a last question that I have for you. In a geometric sequence, the third term is 126 and the 10th term is negative 14. Find the general expression for the sequence. So if you know that you're dealing with a geometric sequence and you're given two kind of points within here, so two terms. So we know term number 3, and that is equal to 126. And we also know term number 10, and that is negative 14. So if you think about this case, so we need term 1, right? Term 2, term 3, okay, and so on. Now, it looks like term 3 is 126, and it's positive. And term 10, okay, within here is negative 14. So it looks like it's going to have an alternating pattern probably between positive and negatives, okay, but we don't know exactly what this ratio is. So we need to know the first term and we need to know what the ratio is. But we know that it's a geometric sequence. So we know that there is a ratio. So what that means is you can write, okay, so we have T3 is equal to, so whatever term 1 was, multiplied by our R, and this was n minus 1, but in our case it's 3 minus 1 because we know what that is. So T1R to the 2. We also know our term 10, and that is again T1R, so 10 minus 1. And this is going to be 9, all right? So now we have these two equations. Now we know term 3 is 126, and we know term 10 is negative 14. So once you have these two equations, you have two equations, two unknowns. We don't know T1 and we don't know R. So you can isolate one of the equations, let's say for T1, and then substitute it in the other. Or you can take a ratio between the two, okay, and then find out what R might be. So for instance, here, what I'm going to do is I'm going to isolate for T1. So T1 is equal to 126 divided by R2. We know that R is not equal to 0, all right? So that's fair game, right? It's not going to cause us any problems. Now we're going to take that, we're going to substitute it in here, and we're going to get negative 14 is equal to 126 divided by R squared. So we're substituting that in. This is R to the 9. Now, simplifying this, well, notice so just exponents, right? So we're going to get negative 14 all over 126. This is going to be R to the 7. So that's that. Taking, so now, we want to be able to solve. So we're going to take the 7th root. So that's going to be the 7th root of negative 14 over 126. All right, so we have that. So that's R. So it's going to be some negative number. Okay, so we're going to have a negative within here. So let's see what that gives us. Okay, so we're going to take the 7th root of, I'll put it in, negative 14 all over 126. And let's see what this gives us. Okay, so it's some ugly number that we have in here. So since it's this ugly number, so what I'm going to do is, actually let me simplify this. So 14, 126, what is that? That's just 1/9. Okay, so this is, let's keep it like this. So this is 1 over 9, that's my R. So I'm not going to use those decimals because I don't want to really write them down. So my R is this ugly number. Okay, so it's this number right here. Now, once we have this, we can substitute it back in and find T1. And you can substitute it in any of the equations. So notice, for instance, here. So T1 is equal to 126 all over whatever R is. So I'm going to substitute that in here. And that's squared. Okay, and we're going to find our T1. So let's see what this gives us. So it's not the prettiest of them all. I'm going to simplify this a little bit for myself. Okay, so we have that, and this is, okay, so 126 divided by, all right, well, since we kind of have the power of this calculator, so I'm going to use that in here. So that's going to be, now the negative, because we're going to be squaring, okay, so that negative is going to be gone. So I'm not going to put the negative in there. So it's going to be the 7th root of, this is 1 over 9, so 1 over 9. Okay, and this whole thing is being squared. Okay, so it's about there. Okay, so that would have been our T1. Okay, so whatever that is, and you can keep it. So it's kind of a mean question because the numbers didn't work out very nicely, but at least you know how to approach it. And hopefully now you know a little bit about the geometric sequence and then how to find the nth term in that particular sequence. All right, thanks for watching. See you in a future video. Bye, everybody.